to go ahead and do a repeated measures ANOVA using the formulas from the Essentials of Statistics textbook. I'm going to try to go a little bit quick to make this a short video, but let's go ahead and get started. The repeated measures ANOVA is just like the other ANOVAs. It's used to see if there's a significant difference somewhere between the means of three or more groups. The difference between repeated measures is that every participant receives all treatments. What's going to change towards the end of the calculations is our within groups terms are going to be replaced with what we're going to call error group terms. So I will explain that to you here towards the end here, but let's get going. Null hypothesis always states the same, that there's no significant difference between any of the means. And the alternative hypothesis says, yes, there is a significant difference in there somewhere. We follow the same source table. We're still going to look for the variance between the groups, but we're going to really focus on the within groups. But we do need to adjust the between group sum of squares by removing the individual differences from all the formulas, which we'll do at the end here. Here's the ANOVA table, or the source table. Let's go ahead and do a real problem now. You got 6 football players from a team, and they're going to test the effectiveness of a new strength-enhancing training program. So each of the 6 players were asked to do as many pull-ups as they possibly could in 10 seconds. Then they had 2 weeks of the training, and then they did the pull-up test again, and then 2 more weeks of training, and then they did the pull-ups again. So here is the results from the training. Okay, from this data, we need to go ahead and calculate some of the stuff out there already. I think you know what to look for. We need to find the means of each group, the totals of each group, and the sum of squares from each group. Remember, the sum of squares is each individual score subtracted from the mean, that difference squared, and then you just add every one of those up, and that's what the sum of squares total is. So the big difference between the repeated measures ANOVA is this. We're going to total up each one of the individuals and get a total for each individual. But the sum of squares between group formula remains the same. You take the total, you square it, divided by the little n, which is the number in each group. Should be familiar with this. If not, please check out the regular one-way ANOVA video. I'm just plugging and chugging here. 6 squared, 18 squared, 24 squared, all divided by 6. Gives us a grand total of 28 for the sum of squares between groups. Now let's do the within groups. Just like the old way, you just get the sum of squares from each one of the groups, add them up. So it's going to be 8 plus 10 plus 10. And that looks like 28 as well. So if we know the two sum of squares, we should know the sum of squares total just by adding them up. So now we have all our sum of squares from the original ANOVA. Let's keep going. Got the sum of squares. Now we need to go look at the degrees of freedom. Degrees of freedom between groups, same way as always. You take the number of different groups, and that is the initial push-ups, 2 weeks training, 4 weeks training. So there's 3 groups minus 1. So there's 2 degrees of freedom between groups. Within groups, you take the number of different groups, which is 3, times the number of individuals in a single group minus 1. That gives us 15. And to find the total degrees of freedom, we just add them all together. So now we know all the degrees of freedom. And the sum of squares from the regular ANOVA. This is where we need to stop. Now we have to make some changes. Because this is a repeated measures ANOVA, this is what we're going to have to do. We need to remove the variance of the individuals. And how we do that is we subtract the individual differences from the denominator of the F ratio. So let's go ahead and do these. The individual differences are called between subjects sum of squares. Do not be confused with between group sum of squares. These are called between subjects sum of squares, only used in repeated measures. This P, if you remember, is the total from each individual. These guys. So let's go ahead and plug and chug. Sum of squares between subjects is 6 squared divided by 3, etc., all the way across, just following the formula. And we get a grand total of 10. So our sum of squares between subjects is 10. So now here's the sum of squares for the error. That equals the sum of squares within group minus the sum of squares between subjects. That's the one we just calculated right there. So we're going to plug in the real values, and we get a grand total of 18 from the sum of squares for the error. Now we need to turn our attention to the degrees of freedom between subjects. And there's the formula for that. It is the number of subjects in a single group minus 1. We have 6 volunteers. Minus 1 is 5. So now we know that. And the degrees of freedom for the error is the degrees of freedom for the within group minus the degrees of freedom from the between subject group, what we just calculated. So let's just plug and chug. And it looks like the degrees of freedom for the error is 10. So now we have all the data we need to go ahead and fill out the source table and figure out what the F-test statistic is. Previously, with the regular Anova, we would take the mean squares between groups divided by the mean squares within group. That would give us our F-test. This is what we used to do, but we don't do that anymore. We no longer use the mean square within group formula. We're going to use the mean square error formula. And we're just going to substitute in the values that we just calculated. So there's the F-test statistic formula with repeated measures. There's the data we need. Let's just go ahead and plug and chug. So the mean squares between group is, just like always, sum of squares between group divided by degrees of freedom by between group. And it looks like a grand total of 14. Moving on to the mean square of errors. It's the sum of square of the error divided by the degrees of freedom of the error. And that looks like it's going to be that. So now we have the data we need to finally get our F-test statistic. It's 14 divided by 1.8. Comes out to with a F-test statistic, or an F ratio, of 7.78. Everything from here on is pretty much just like the regular one-way ANOVA, but let's go ahead and knock this out. We need to compare our calculated F ratio with the critical F ratio in the book by looking up the number of degrees of freedom from between group and the degrees of freedom from the error term. And from our data, it looks like we're looking up the critical value at 2, 10. And we got a couple of numbers there. The 05 alpha level states that we should have gotten a calculated F value of 4.10 or smaller if the null hypothesis were true, and ours is bigger than that. And at the 01 level, we should have got a 7.56 or smaller. Ours is still bigger than that, too. So what that means is we're significant at the 5% level and the 1% level. So our calculated F is greater than the critical F from the back of the book, so therefore we get to reject the null. And that's all there is to it. Hope you enjoyed it. MGZ out.